about it. I mean, I've been running this company for now, it'll be 40 years later this year, and it's been a good life. Before I did this company, I was an academic, but when I was 21 years old, I started my first company that was a spin-off. I was at Caltech at the time, and I had all kinds of crazy intellectual property issues with Caltech. But anyway, started this company, got venture capital, brought in sort of professional management type people. It was, the main thing that I learned was I kept on thinking, this is what we should do. They kept on saying, no, we should do the exact opposite. It would turn out I was right, which I didn't really want, because it was kind of like, that wasn't what the part of the thing I was supposed to be doing. This is all 1982, 1983 type time frame. Actually, somewhat amusingly, that company was originally called Computer Mathematics Corporation. And when it got venture capital, our fine VCs said, you know what you guys should be into? You should be into AI. This was 1982. And the company got renamed to be called Inference Corporation, which was very modern for 1982. Yeah. And then actually it went through, I had thought that it had actually gone through all the letters of the alphabet in rounds of financing. But I sort of detached from the whole thing after a few years. But the company kept going, and eventually it went public sometime, and it went public in the mid-1990s. And actually it was the 30th anniversary of it going public was recently. This is a long, shaggy story. And so I had never looked at its filings from that IPO, because at that time I was doing my own company, and I really wasn't that interested. I was just like, register my stock and get it sold type thing. And I was surprised that it was they had only got to, I think they got to J in letters.
Series J.
Series J. So I was wrong in my long-term claim that they ran out of letters of the alphabet. But
what do they do? What is this company doing?
Well, they were, they went public in the mid-90s, and they were bought by somebody else and bought by somebody else, and who knows where their scraps ended up. Originally, they were doing early expert systems AI. And they were based on a bunch of tech of mine and some other tech that they brought in. And okay, so that was my first experience of doing a traditional company, although in those days, venture capitalists were only to be found in New York and things like that. There weren't Silicon Valley venture capitalists yet. Okay, so that had been my previous experience. Then I was, and it was a hobby when I was doing science in the 80s. I also did sort of strategy consulting for tech companies, which was very educational. And so then when I came to start my current company in 1986, I was like, let me just see if I can do this myself. And, I didn't, I've been the CEO, and I've had great people I've worked with all those years, but I've never really had it's sort of a pity. I've never really had kind of a business partner for the whole thing. And, the company is not, I kept it comparatively small. It's about 800 people right now, which is not tiny by today's standards. We've been lucky enough to be profitable every year for the last 38 years. So, which is mostly achieved by spending less than you make, which is sometimes, which is a very rare. I know it's not really the theory around here. It means that we have a lot of very talented people around the world. It's been a very geo-distributed company for a long time. So, when the pandemic happened, it had basically no effect on us. I felt kind of guilty that it had really no effect. And I think, that's so. And the things we've been doing. I think, as you observe, we have built a piece of software that has remained very consistent over a long period of time. I think the greatest value probably is kind of the design of the system, and kind of, we also have invented tons of algorithms and things along the way, which the world doesn't know how they work. They just work in our system.
Is there something, do you think there are some things you were able to do because it was completely independent that you wouldn't be doing if it was VC funding?
Absolutely, yes. We do lots of projects that are 10-year projects, and it doesn't really and I make lots of, we do projects which seemed completely impossible. Like, for example, the Wolfram Alpha project was one that sort of was like, that's a crazy project.
Yeah.
Even my internal team said that's a crazy project. In fact, the way I had to do that project was as kind of it helped that we were a geo-distributed company. I kind of hid a couple of hundred employees working on that project, which turned out to be the right strategy because the rest of my management team really didn't believe in this project. And they were right that before it was demoable, there was nothing to believe in. Once it was demoable, it took them only about half an hour to be like, oh, this is pretty good. This is pretty nice. We can do something with this. But it would have been killed if it had been, left out exposed, so to speak.
Yeah. One actually unique thing about Wolfram, there is this channel, and you can see live CEOing. And right now it's episode 976 or something. So is it like almost 1,000 episodes?
I don't know, actually. I haven't been counting. This was a thing we started doing probably 7 or 8 years ago. We do these internal software design reviews. I think they're kind of interesting. It is cool when our users and experts in different areas can kind of see what we're figuring out and can give input. And it's been, I've been surprised that other people haven't done this. I mean,
maybe in a public company, people have a hard time. Like a CEO can just say, and I'm going to live stream myself on Twitch.
Yes, right.
Yeah, I'm actually curious. So there's already 900 episodes. Conceptually, in near future, you could be able to like prompt it, put it into AI, and say, continue doing my job. And I'm kind of curious, if we get to a point where it can do most of it, would you still like to continue doing it, or is it like the work you would like outsource? It's like now this agent.
I have been my life has been about get the best tools one can and then do the things that one is then enabled to do by those tools. So back when I was a kid, I started using computers to do physics, and I could never really understand why other people who were doing physics didn't use computers to do it. And that gave me a completely unfair advantage back in the late 70s, this is, at doing particle physics in that case. And it's been my general theory is use the best tools one can to do things. And, I think it's still the case that, us humans, there are an infinite number of things one might do. We humans get to figure out what it is that we actually care about doing. And that's a thing that we can keep on doing, even if, I view myself as having kind of, in a sense, lived the AI dream for decades, because I've been interested in taking ideas I have and turning them into real things as efficiently as possible. And I built a lot of tooling to do that. And that's, so when I think of something, I type Wolfram language code, and then, 10 minutes later, I have some thing that I can work out from that. Yes, I try using agents to generate that code. If I was less expert at doing it, they would probably be more useful. The fact is, at this point, it is much faster for me to go from things I think of in my mind to just start typing, because I can do that before I could even explain to somebody what it is. If I had to say, describe in English what you're about to do, I would have a hard time doing that.
Yeah, it probably helps that the API remained consistent, so you could memorize it.
Indeed.
In open source, even in Python, at some point they decided, let's change how print works. And it's like a single, very annoying change. It just invalidated a whole bunch of code bases.
Right.
Yeah, so actually, Mathematica, I noticed it's the first tool I used which actually integrated LLMs. So I was surprised that it was like the first one. And there's this Wolfram LLM benchmarking project which tries exercises from on your book and says how accurate they are. And it went from 40% a year and a half ago to 72%. And maybe conceivably in near future it'll be 100%. How do you think this will change?
Oh, I mean, those benchmarks are now gamed. So those benchmarks are old.
I always assume that it's obscure enough where people will not bother actually optimizing for Wolfram LLM benchmark. So for me, it was like the ground truth.
Yes. I'm afraid that's not true anymore.
Really? Oh, crap.
So it's every corner is something people start to sort of think is important to. But I think in terms of, so for example, right now, there are a bunch of things in my world for which LLMs are kind of interesting. Like, for example, one thing, okay, so another part of my life is thinking about fundamental science, and in particular made this big breakthrough about 6 years ago now in figuring out fundamental theory of physics. And one of the questions there is, okay, so we think we have a fundamental theory of physics. Can we find experimental evidence for or against it? And so that's a place where one might say, well, let me invent a kind of evidence, something where we could do an experiment. It'll cost $1 billion to do the experiment. Okay, maybe somebody will do it. But a much better scenario is there was some experiment that was already done in 1985 or something, which got weird results. And they were just sort of reported somewhere in the literature and people ignored them. Can one trawl for that? The cautionary tale, so to speak, is back in the 1800s, people wondered, did molecules exist? And, people didn't know. And, there was, but it turned out 1827, Brownian motion had been discovered by some botanist. It looked through a microscope, so these little pollen grains being kicked around discreetly. But that connection was not made for 80 years. And, so the question, an example of an LLM use case for me is, thematically trawl the literature of physics to find things which are relevant for understanding whether space is discrete and things like this. There's one use case. I mean,
makes sense.
Can I ask a question?
Yeah, go for it.
In that use case, do you think that it is primary access to the knowledge, right? Like having just all of the knowledge, or is it something fundamental about the way the LLM is accessing it to draw connections?
I think that the issue is thematic searching. That is, we've been able to do keyword searching, back into the 70s for the scientific literature. But what's true now is you say, I haven't managed to make this work very well yet. So, okay, so I'm not... yeah, well, right. But I think it has a reasonable chance. You say, where's a place where there's some discrete thing that was observed in this or that thing, and it's not, the words are not going to be there, it's going to be a concept, and there is a fighting chance that, it's just like, what we've had with numerical data, we can do statistics, we know how to, find means and variances and all that kind of thing. For textual data, we have not had those same kinds of tools where you can say, what's the average thing that gets said here? We don't yet know formally how to make that work, but we now at least have a tool that lets one get to that kind of question. So that's, I think, to me, the question of how LLMs actually work is an interesting question about which remarkably little is being done. With all the people, you would think, with all those people who, it's a difficult problem. How, what is really going on? Why does machine learning actually work? What can you learn with a neural net, for example? Can you characterize what kinds of things you can learn? Can you learn anything? Probably not. Can you learn the kinds of things that humans can learn? Perhaps yes. I think I have some theory actually now of why these things work. This is taking off in a different direction, but please go on. We can talk about that.
Yeah, so you had a blog post in 2023, how LLMs work, and in the last couple of years, there's been maybe some extra changes. People are doing more agentic applications. I actually have an application where I'm asking, putting all the context in an agent, and I'm asking, who should I meet at this party? But I'm just curious, have your opinion changed in the last 2 years? Maybe in that blog post, it was more framed as more a Markov chain kind of thing, kind of just simulating it. Do you still have this opinion, or have it changed?
Well, I think, at that point it was next token prediction.
Right.
Now it's kind of next task prediction. It's kind of gone up a level in abstraction. It's kind of like, rather than what token should I emit next, it's what piece of some task should I do next. And I think, it seems to be, that's one thing. The other thing that's happened is this ability to kind of loop around and say, and rather than in sort of training, in real time, say, did I get there yet? If not, let me retry it. And the thing that's surprising, that I think one doesn't understand very well, is how powerful that process actually is. That is, if we look at, good analogy, biological evolution, which just tries random things and sees what happens. And 10 to the 40th organisms later, of individual organisms that have lived in the history of life on Earth, there's us type thing. And the question is, why does that work? And then what is something similar going on when you see kind of the agents are going off and doing random things, they don't quite work, and then they try again, and then they make something work. I think what's happening is, so, my current kind of meta theory of what's going on is it's actually something very similar to what happens in biological evolution. The question, okay, so backing up a little bit, spent a bunch of my life studying what I now call Ruology, the study of simple rules and what they do. So you might have thought, if you just write down some tiny little, one-line program, that no one-line program would ever do anything terribly interesting. This turns out not to be the case. And, I studied back in the 80s lots of systems that, lots of very tiny programs, particularly these cellular automaton systems, where tiny program goes in, very complicated behavior comes out. I think that is the main secret that gets us kind of complexity in nature, but it's also a thing that, it's this great power of computation that isn't what we normally harness, because normally when we are doing computation, we are writing code where we can foresee what that code is supposed to do. Whereas in the computational universe of all possible programs, even these little tiny programs do all kinds of complicated things. They do complicated things for which we don't necessarily have a purpose, but they just do those things. So I think the thing that's happening both in biological evolution and in machine learning is we're getting to harness kind of the power of what is possible in the computational universe. So in other words, what happens in like biological evolution is you keep sort of iterating, can I find a program that does this? Well, you do. Those programs do that thing often in this incredibly ornate, complicated way. They do not do it in an engineer's kind of way of this is the mechanism, now I can see what's happening. They put together these sort of random pieces of irreducible computation that happen to do the thing you want them to do. And that means that, that's why when you look at biomedicine or something, things look really complicated. We don't do the things we do in the obvious, simple engineering way. We do them in this way that happen to be found and happens to work. And I think the exact same thing is going on in machine learning, and I've got, I think, pretty decent evidence of that, that really what's happening is, the big surprise is that there is so much potential in the computational universe that you can get very sophisticated tasks done by just mining random pieces of that. It's something that's sort of unintuitive that you can get, even though this piece of computation is sort of incomprehensible in how it works, it does this weird thing, you can get enough of those pieces to put them together to do the tasks you want. And I kind of think that's what's fundamentally happening.
Yeah, so great. Speaking of rules, something I wanted to learn more about. So in 2020, you launched the Wolfram Physics project. So the idea of applying this idea of Ruology to the physical universe, do you have anything to say about it? So I'm curious, what was the motivation? What happened in the last 6 years? How do you feel about it now?
Well, having discovered that very simple rules can do very complicated things, you kind of have to wonder about the universe. And I had, historically, long ago, in antiquity, people were arguing, is the universe discrete or continuous? That argument continued until the end of the 19th century, when it became clear that matter is discrete. It's made of molecules. People didn't know whether space was discrete. Early part of the 20th century, most physicists believed that space was discrete. They couldn't make it work. They basically didn't have the tools. Some of them even knew that the tools were lacking for doing that. 100 years later, thought about this again, you can realize that, yes, in fact, it does make sense for space to be discrete, and you can kind of make models of that, and they're very computational models. And so early 1990s, I had done a bunch of work on this. Then I packaged it all up in it was one small part of a big book I wrote called The New Kind of Science. And I was a little disappointed that my friends in physics, I had been I would say, a leading physics operative back in the late 1970s, early 1980s. And then they were sort of disappointed that I kind of left their field. But then, when I put sort of half a chapter of this big book about sort of how you can think about fundamental physics in computational terms, and my friends in physics were like, we don't need this, we have string theory, it's going to solve everything. It's the market there was not a good product market fit at that time, so to speak. So then 20 years go by, and then I kind of made a little technical breakthrough in figuring out more about how this could work. And a couple of young physicists were like, you've really got to work on this. It's irresponsible not to do it. So we started in 2019 trying to see whether we could make this kind of computational model for foundations of physics. And to my great surprise, it worked vastly better than I'd imagined. I thought that a lot of issues that would be, 50 years away, we just were able to nail. We'd solve them. Now, then, unfortunately, you have to rebuild sort of all of mathematics from geometry on up to really see how this all works in detail. And that's a lot of work. And we've been steadily picking away at that. What ended up happening is that the methods from that physics project have been applicable to a lot of other fields, like these things in machine learning and in biology and so on. And so I've been a bit distracted because there's a bunch of very low-hanging fruit to be picked using these methods in other fields. But we've been, for example, a big project right now is what we call infrageometry, which is usually in geometry and things like differential geometry, you're looking at calculus, where you're looking at continuous space, little pieces of Euclidean space and so on. And for us, we have these hypergraphs underneath, so it's not Euclidean space at the end. So you have to kind of rebuild all of the ideas about how geometry works. And it's a bunch of work. We were having LLMs try and help us. They've been semi-helpful.
Semi-helpful? I think somebody here also was wondering about hypergraphs. I forgot who it was. Oh, that was you. Yeah.
Observer theory evolved from that.
Oh boy. Okay. Well, this is a deep, deep rabbit hole. So let me see. The first question is, what is space made of? And in the past, people have just said space is made of anything. You just put stuff in different places in space. In our models, space is made of discrete atoms of space, where the only thing you can say about them is how they're related to other atoms of space. And so you can represent that by a hypergraph, where you have, an ordinary graph. Every edge in the graph has just two ends. In a hypergraph, you can have any number of things related by a hyperedge. So in any case, you then have the idea that sort of in the universe, the only thing that exists is this giant hypergraph. And everything about the universe is just a feature of that giant hypergraph. And the thing progresses by rewriting little pieces of the hypergraph with other pieces of hypergraph, and that's kind of the progress of time. And then what's very non-trivial is that, much like when you start with molecular dynamics and you see what happens with a whole bunch of molecules bouncing around on a large scale, that gives you things like fluid mechanics. What turns out to be the case when you start off with this hypergraph, on a large scale, it gives you the structure of space-time. So that's kind of the first kind of big deal. Then it gives you a bunch of things about quantum mechanics. And it seems like it gives you the things that we know are true in physics. And then the question that arises, one of the questions that arises is, okay, so there's some discrete hypergraph rewriting rule that gives you the things that we see in physics. Why did our universe get that rule and not another rule? And so that confused me for a long time. And then I realized, actually, in effect, all possible rules are being run. It is just that we, as observers of a certain type, are only sensitive to certain aspects of what's happening. So it's like in fluid mechanics. If we were little molecular scale creatures, we would be like, oh, I can see what this particular molecule is doing, that particular molecule is doing, as opposed to the way we actually are, which is, we're observers that don't follow all of those little microscopic details. We just say, oh, it looks like a fluid that's flowing. And so for us, the laws of fluid mechanics are the way they are because we are observers of the kind we are. If we were a different kind of observer, we will believe different things about fluids. And the big thing has been that seems to be what's happening throughout physics. And so the big surprise is that we can derive laws of physics, like laws about gravity and quantum mechanics and so on, from the fact that if we are observers of the kind we are, then inevitably it is the case that we must observe the kinds of things that we know are the way that the laws of physics work. That's a very quick version of this whole story.
I guess I was really curious about where that computation lives. In the hypergraph, I'm already an observer in the graph, a property of the graph, and time is also an emergent property.
Yes.
This computation step requires.
Okay, this is a confusion that is this is a very interesting confusion people have, which is, if the thing is a computation, where is that computation running, so to speak? Okay, so this is a thing which, in the history of philosophy, people have been confused about this issue over and over and over again in different forms. What is it? The fact is, what we're doing is the universe does what it does. We are merely finding a description of what it does, and the description that we find is a description in terms of hypergraphs and so on that's convenient for us. You know, what science does is it tries to take what the universe actually is doing and find a narrative about what the universe is doing that we can understand in our minds. And so saying there's these hypergraphs and they're being rewritten and so on, that's our description of what the universe is doing, so to speak. There's nothing that is driving, there's nothing underneath that that is sort of running the hypergraph. We can run a simulation of the hypergraph, but the universe, this is just a description of what the universe does. It's not a thing that, so, right, it's not a thing. And the question, you can ask the question, why is the universe doing anything? Why does the universe exist? That's a question which we can actually make some statements about, which is, it's not what I was expecting to talk about here, but anyway, this is, you know, it's a thing that's been, basically this thing we call the Ruology, which is this limit of all possible computational processes. This is an inevitable object. Like once you have the idea of computation, this exists in the same sense that once you have kind of the idea of addition, you can say that 1 + 1 = 2, so to speak. It's not, you don't need 2 pebbles to say that 1 + 1 = 2. It's an abstract thing. And so it is with this, and so you can, well, there's a whole set of arguments about whether it is a contingent fact that there are observers of the kind we are, just like it's a contingent fact that we live on this planet rather than on some other planet. But once you know that fact, it then follows that things have to work the way that they work for us, so to speak. This is a deep rabbit hole. I'm sorry. It's a strange thing because I spend part of my time running a tech company, part of my time doing basic science, and recently I've been dragged into spending part of my time talking to philosophers because it turns out that a bunch of the things that we've done in our physics project and so on are of high interest to the kind of traditional philosophy community, because there are a lot of questions about metaphysics, for example, where people have been like debating this, as I now learn, for 1,000 years. And we can actually say something definite about these questions. And it's been kind of neat that a bunch of people who've been thinking about those things have gotten excited about this. And so it's a little bit of a strange kind of life trajectory that one ends up thinking about, the practicalities of how our technology is relevant for AIs as well as for humans and so on, as well as thinking about these questions about metaphysics. I mean, I would say that one of the things I'm realizing in recent times is that sort of low-level programming I have believed should not exist for 40 years. I mean, we've kind of, for myself, I haven't done low-level programming in 40 years. I mean, I was a little bit horrified to find out that a bunch of code I wrote for the original version of Mathematica is still running inside there. So, and I'm like, can it really be? And it's like, it's actually really quite good, I'm told. So, but that's, I was pushing to try and get it rewritten by LLMs, but I'm being told that it's actually not. It's not going to help.
I see.
But the question of it's kind of like what we went to a lot of effort. We've gone to a lot of effort over the years to design this language that allows one to have sort of a way of expressing computational thoughts efficiently, and one of the purposes is to have a language which humans can read as well as write. So it's just like if you're doing math, you could just do math with words, but actually mathematical notation is a pretty good idea because it allows you to kind of streamline your thinking about math. Kind of my way of thinking about what I've been trying to do for years with Wolfram language is to do the same kind of thing for what you can think about computationally. And sort of the claim is, just as sort of the mathematical sciences could get started, one can kind of start computational X if one has the right kind of language and notation for doing that. But the thing that's interesting right now is that I think the niche that I'm increasingly understanding we sort of uniquely fill is if you want to understand what you are computing, then we have kind of the thing that lets you do that. So in other words, if some computation is going to happen under the hood and it's going to be run in Python or Java or whatever else, you don't really care. It doesn't really matter to you what's running underneath. But if you actually are in a business, which not everybody is, But if you're trying to build sort of a tower of capability, you kind of, at some point, you have to understand what you are computing. And the effort that I put in the last 40 years or so into building a language that allows one to express computation in a way so that humans, I hope, can understand what they're computing, that seems to be a pretty useful thing.
Yeah. I'm actually curious. So I know some companies are rapidly adopting AI, so they have AI write a bunch of code, but sometimes they regret it. So Amazon recently, they realized there was so much AI code, the stability went down. So now every change needs 2 human reviewers. So I'm wondering, has this AI code writing been used at Wolfram Research? Are you using it? Are you restricting it?
You know, we have less need for it than many because most of our code is written in Wolfram language, and it's pretty, you know, direct thought to code type stuff. So in other words, if you, by the time you have crystallized your thought, you've probably written the code for it. If you have not crystallized your thoughts, you couldn't write the code, you didn't write the code. We do have a bunch of lower level programming that, you know, dealing with all kinds of practical systems type things. And I've been pushing pretty hard to replace a lot of what we've been doing there because it's, you know, whenever there is a clear definition of success, then you're in good shape. I mean, you know, my general rule is if you have a task for which 80% success is success, then using AI, machine learning type stuff is a win. I mean, if you're, you know, if you're trying to, I don't know, you know, rank search results or something, and out of the 10 search results, one of them is exactly what you want, then it's a win. If you are trying to, you know, build something in a big tower where you need it precisely right and you can't check that, then it's a lose. But there are plenty, you know, there are plenty of places where, you know, we can tell whether it worked, you know, and it's, you know, it's fairly easy to verify that it worked. And in those cases, we can use it. I mean, we even, actually in the new version, there are even a few mathematical functions that use AI stuff inside. So, for example, solving differential equations. Most of the time, okay, doing integrals, we don't need it because we have sort of industrial methods for doing that that are vastly more efficient than what we can find there. But differential equations are still a bit on the edge of what are possible. And so there are places where it's useful to have the AI go and try this, try that. It knows that sort of from the literature and so on. And it's very easy to check whether it's right. And sometimes, and it's right enough of the time that it's worth trying that method alongside other methods. And I don't know what, I mean, you know, there's this whole, I would say it's kind of corpus-based algorithms where the knowledge of the world, I mean, we've spent a lot of effort sort of systematizing certain kinds of knowledge in the world, but there are things where there's just, like for example, the thing from years ago in Wolfram Alpha actually is, you know, you type in some random unit conversion and it tells you, oh, that thing you typed in is about 75 centimeters, let's say. It doesn't tell you it is, you know, 75 million microns because nobody would ever say that. And that's something we learnt years ago, 20 years, 15 years, no, 18 years ago. We just sort of ground up the literature and found for every unit what prefactors do people typically use for that unit. So that's it. So then you can kind of bottle up that kind of thing that comes from sort of the average of what the world thinks and turn that into, in that particular case, an algorithm and just use it.
Yeah, makes sense. Actually, one thing I remembered I wanted to ask you, like 5 years ago, 10 years ago, there was a post where you described your personal productivity platform where you actually recorded every keystroke you've ever pressed since 1980s, I guess. I'm just curious, are you still doing it? Have you found something cool to do with this data?
Not particularly. I mean, I think, you know, I record enough of that stuff. I do enough yakking on live streams and so on that there's an awful lot of me that's kind of out there, sort of exposed as digital exhaust. And I don't know, various people have tried to make kind of avatars of me, which so far are a bit disappointing. I mean, so far the main disappointment, like one of them was my staff had sort of interacted with this thing. They did it pretty good. So I did a live stream with it, and it was pretty bad, I thought. And I was disappointed by the difference between, you know, my staff's perception of me and versus it and my perception of it. But no, I find, I mean, you know, occasionally I'll do some sort of analytical thing with all the data that I've collected. It's easy to collect. And it's, I mean, I did realize that, it helps if you have your own company and you have sysadmins who work with you, because these things break all the time, and they get fixed, and if one couldn't be bothered to fix them, then the data would just disappear. But yeah, it's I mean, the thing that, like every time somebody sends me an email, for example, I get some, immediately in the thread, I get some trace back of, previous interactions I've had with this person going back, whatever, 30, 40 years. And that's very useful. It's very, it really helps. Otherwise I'm like, I have a pretty decent human memory, but this is it really, really helps that. Yep.
Oh, great. So yeah, I've really enjoyed watching you as a science operator in the world over my lifetime. Also exposed to Mathematica at a very early stage in school, and all the way through watching your big fights. I think of them as like prize fights between you and physics, between you and so-and-so, and you, no. And
I don't view them that way, by the way.
So that's my question. I think one of the things that makes you so unique and interesting and worth observing and listening to is your ideas have a quality that sets them apart. They're, you could say they're iconoclastic, but I think it's more subtle than that. And I've always been curious where that's coming from. Are you seeking, do you have a local algorithm that you're following that leads you to push on ideas that have this kind of friction with status quo? Is it more of a downstream, just a stylistic personality thing? Or do you even agree that there's even an outlier amount of clashing in your career?
Yeah, I don't see that particularly, and I don't really, and I also, maybe I don't care it that much. I mean, for me, the driving force tends to be, I like understanding things at sort of a foundational level, and I'm kind of like, when I see, I could actually understand something about the foundations of biology or something, that's very motivating and interesting, and I try and do it. And in terms of things I build, I like to build these kind of sort of alien artifacts of things which are, one didn't imagine could exist, but one manages to build it. I find that rather satisfying. Whenever I'm in a situation where it's kind of like, I'm in a competition with this or that other thing, I'm like, I don't want to do this. I mean, I learned that. I happened to be involved in particle physics when I was a kid. There was a field that was particle physics in the late 1970s was AI in 2025 or 2026 or something. It was the hot place where lots of stuff was happening and everybody was and it was a somewhat competitive field. And my main psychological reaction to that was whenever there was something where I was doing something and then 5 other people were also doing that same thing, it's like, I don't care about doing this. I just let them do it. It's not that interesting. It doesn't, I suppose, I don't know whether it's a piece of egotism or something else, but I like doing things which other people aren't interested in doing, so to speak. And that's been, and then, you have this trade-off. If you do things which nobody else is interested in doing, then once you've done it, even if you're very pleased with what you did, you have to kind of tell people, if you want anybody else to pay attention, you have to kind of do a certain amount of marketing of the ideas for anybody to even notice them. I think, look, I've been in terms of what is one's, like, I've never read the reviews of my New Kind of Science book. So it's probably good. I don't know. I think I just what I learned about those kinds of things years ago is you read something good, you're like, oh really? Do they really understand what I'm doing? They don't really understand what I'm doing, but they wrote something nice. That's nice. You read something bad, they don't understand what I'm doing, and I'm kind of annoyed because they're kind of attacking it. It doesn't want no good. And I think that my I would say that another thing I sort of, so I mean, something I realized only rather recently, which is kind of embarrassing, it took me so long to realize, is that most fields in science, for example, the people who do them are people who've been in that social milieu for a long time. And the idea that somebody just sort of shows up one day and does something in field X when they haven't kind of been in that social milieu for decades is very unusual. And I've done it a bunch of times. And I would say that has been less of a problem in the last couple of decades or so, because, I'm probably better known. That helps in it being less bizarre that I'm doing some random thing in, you know, foundations of biology or something, because it's kind of like, it's not like somebody just appeared out of nowhere. It's like, it's at least a known person who is sort of known for other stuff. But you know, as far as, I mean, the thing that's, you know, I don't, you know, in terms of people, I mean, there are a lot of very bizarre things that happen when you know, for example, my new kind of science book, one of the things that in most areas, I would say people liked it a lot. The one area where people were very sort of antagonistic was in physics, which was very bizarre because I was a well-known person in physics. Not only that, but also essentially all of those people who were like, oh, this is terrible, use our software every day, which is just the weirdest thing. And it's like you know, oh, we use the software and it's really good and it's really useful to us, but you know, the person who's sort of behind this is saying things about physics and they couldn't possibly be true. It's a bit of a strange cognitive, you know, jump. But I have to say, in recent years, that whole story has, you know, in our recent physics project, I would say that the reaction of physicists has been largely positive. If, you know, because, and what happens, and this is true in many fields and companies as well, you know, fields go through these periods of high arrogance where, you know, it's like in physics in the, you know, end of the 1990s, it's like string theory, we're going to get it. You know, we really know what we're doing and we don't need anything else. And then I remember when Wolfram Alpha came out, I wondered what the AI community, this was, in, oh my God, 2009. You know, the AI community was at a very low ebb at that time. And it was kind of, you know, what would the AI community think of this? I was curious, because it was kind of, people had been talking about question answering systems for decades, and nobody had managed to make it work. I had the interesting experience, I was at some random event a couple of weeks before we released Wolfram Alpha with Marvin Minsky, who was a well-known AI operative.
You created, I guess, the first day of winter?
Yes.
Already got paper showing you can't...
Well, the perceptrons can't work, which is kind of a funny thing to have shown. But, I mean, that was an interesting cautionary tale for many reasons in kind of the history of ideas. Because, you know, what happened is, okay, history of neural nets. People had actually talked about neural nets in the 1800s, and people even had thought of the fact that, you know, the brain was full of wire-like stuff. That wire-like stuff might be doing logic-like things. I haven't traced this history completely, but in the 1870s, people were already talking about that. 1943, McCulloch and Pitts wrote this big paper about sort of connecting Turing machine-like things to neural nets. I've been trying to trace that history, actually, because I was interested in these discrete neural nets, and I wanted to know, why did people ever think that neural nets were continuous? This tracing of history actually led me to the granddaughter of Warren McCulloch and the farm she has, where she says, I have all these papers. I don't know what to do with them. So I went, about a year ago, I went through a bunch of interesting Warren McCulloch papers. So I know a bunch about this history. Pretty much. Walter Pitts was this young, kind of hotshot, kind of precocious math person, and he had been working on matrices with a chap called Householder. And so he was really into matrices and all the things you could do. The matrices were very high tech in those days, and that was why he kind of thought of doing that, and that's you know. And then by the time, you know. Then, 1957, Frank Rosenblatt invents perceptrons. A story I've still been trying to trace is the animosity between Marvin Minsky and Frank Rosenblatt when they were in high school together, which there is a story there, but I don't yet know what it is. But anyway, then Marvin, along with Seymour Papert, in the early 60s, figures out that one-layer perceptrons can be completely cracked mathematically. And so then, in the brilliance of the world, people say, oh, that means perceptrons can't do anything interesting. Game's over. And then in the beginning of the 80s, people kind of started looking at that again. And I looked at that time and, you know, played around with neural nets and said, I can't really see how to make these do anything terribly interesting. But let's see, but you got me into this rabbit hole because you were asking.
I had a personal funny story. I was at Google Street View in 2011 and 2012, and I took a class in deep learning, and I'm like, hey, let's get it working in Street View, and people are like, no, we tried neural networks in the 80s, they don't work. So I really had to fight hard against it. I actually had to implement it myself because nobody else wanted to work on it. Yeah.
No, I mean, well, how do we get into this particular rabbit hole?
I asked of you said about Marvin Minsky.
Oh, yeah. Yes, thank you. Sorry. So, you know, Wolfram Alpha is about to come out. I'm at some random event with Marvin. I say, Marvin, let me give you a demo of this thing we built. It's like, what is it? It's a question answering system, among other things. Says, okay, sure. Looks at it for about 2 seconds and then wants to talk about something different. I said, Marvin, you should actually look carefully because it actually works. He's like types in a few more things, and then he's like, oh my God, it actually works. And then he's running around the room telling everybody else, you've got to look at this, it actually works. So what happened, which was kind of interesting, was AI was in a sufficiently low ebb at that time that the people who were in that business were really pretty happy that we'd managed to make something work, even though I would make no claim that the way that Wolfram Alpha works is any kind of brain-like AI type of thing. It's a bunch of algorithms, and some kind of clever algorithms, but algorithms nevertheless. It's not, you know, there's no kind of, this is imitating a brain. I mean, I think so. That's a case where that was a very low self-esteem field that was very happy to see something from the outside come in. So really, it depends on, and you know, like right now, in biology, for example, people know there's a ton of data and no theory. And you know, that's a known thing. And so, you know, there is interest in seeing how one can make a theory in biology, because there really isn't much that's been, I mean, we're now starting to figure out some things I think are fairly interesting. But
makes sense. I think I saw a question in the back. Is it still?
So long time fan. You know, with the Ruology, oh, here we go. Yeah, so if I'm following correctly, right, you have laws, which are sort of macroscopic at a human scale, and then you have rules, which are these, like, you know, very fine-grained things. And it seems like you just have this very strong conviction that underlying everything, there's a certain elegance. And as a software engineer, of course, I want there to be an underlying elegance as well. But where does this persistent conviction and belief come from? You said you think it earlier, like today. I'm just curious, yeah, if you could sort of expand why you believe that.
Okay, so I'm not sure that in a sense, the Ruology has both simplicity and arbitrary messiness in it. And so it's, you know, the idea, so one question is, should the universe be explainable? Should there be anything we can say about how the universe works that would be understandable to us? Or is the universe just, you know, we'll never understand it type thing? You know, if you look in the history of philosophy and thought in general, you know, there have been waves of time when people have thought, you know, we're going to understand the universe. For the last, I don't know, 50 years or so, there's been quite a lot of pessimism about that, because it seemed like, you know, every time you get to another level of particle physics, it's more complicated, et cetera, et cetera, et cetera. You know, the question of should there be some underlying machine code that is, you know, accessible to us in some way, you know, it would be nice if that was the case. I think, you know, the question of, is there a simple rule that governs the universe? What happens with this Ruology object is that's not really a question that makes sense to ask, because the Ruology contains all possible rules, and the issue is, for observers like us, what part of that space of possible rules do we get to sample? And the things that we sample about it actually work that way. We can attribute a bunch of different rules to the universe and get the same observed results.
So when you frame it as a should, right? To me, what this is saying at a philosophical level is that you feel like there's maybe utility to that kind of wish casting, maybe, right? Like it's a worse world if you don't believe that the universe is explainable, right?
Right. I mean, if we cannot, okay, we could live in a world where absolutely nothing is predictable. You know, what happens day to day is, you know, determined by random fate, and there's nothing predictable about what goes on. You know, it is, I think that's, you know, it would be, I don't know, for us humans, you know, our idea of consciousness even is very much associated with this kind of thread persistent thread of experience that we have. If we can't have a persistent thread of experience, it isn't really us. If it's just sort of something random and different every day, we don't have that same it's not the same experience that we have. I kind of like that experience, so it's a good thing if we can find a way to navigate the universe so that we can have a predictable kind of predictable experience. I mean, that
sounds great to me. I mean, it's just we're living in a moment where, like, we're shipping code that we don't read all of a sudden, and also Mark Andreessen is like saying, "Hey, self-awareness is overrated," So,
Well, I think the thing to understand is that we get worried about the fact that we have computations going on that we don't understand, and it has only been an anomaly of 150 years that we've been able to understand the stuff that we use. So in other words, post-industrial revolution, you could actually see the cogs and the levers and so on. You could see how the machine worked. Before that time, if you wanted to get stuff from here to there, you might use a donkey. And you know what the donkey does, but you have no idea how the donkey works inside. You don't really care. And it's also the case, in the natural world, we have all kinds of things that are going on in the natural world, which we try with science to understand something about how they work, but it just does what it does. It has been an anomalous period that we've been able to understand the machinery that we use to do things, and we don't understand. For example, in biology, we don't understand the machinery that is us, so to speak. So I think it's this question of can one sort of live a reasonable life without understanding everything about how things work? The answer, historically, has certainly been yes. Although science is kind of great if one can figure things out with science and have things be more predictable and so on.
Amen to that. All right, thank you.
I'll have one more question, and then we'll wrap up. 2 more questions. Let's quick. Marissa.
Hi, I'm Marissa, and I just want to personally thank you. When I was in college, I remember using like Wolfram Alpha and all the software suite, and this was 2010, 2014 areas, so obviously you've been like pioneers of computational thinking, and now some of us who are starting with like different ideas, and we wanted to do like startup, and you have successfully navigated 30, 40 years of really successful company. Do you have that like simple rules or the universal laws that you've embraced all this time, and even through like the most challenging times to be this successful, and what kind of
I mean, I tend to like to understand stuff, and that's been a very useful trait in doing business as well as doing science. It's kind of, what's the main point? What is there's all kinds of sort of expert things you can say and do and whatever else, but it's like actually try and drill down and understand what is the essential point. And that's, and actually understand it. And I think in running a business, I will say that any aspect of our business where I don't really understand it typically doesn't go very well. And, it's while I'm not actually doing the stuff on the ground, if I don't understand it, it's not going to work well. And I think that my theory of the case is that sort of this foundational thinking about things is really, really useful, and is something that survives, even when the AIs are doing all of the mechanism for you. Sort of foundationally understanding what's going on is kind of really pretty important. That's my 2 cents worth, anyway. I think maybe there was one.
Thank you. So you said that generally speaking, physicists kind of reacted positively to what Wolfram Physics is doing. I was wondering if you could elaborate on this, because some of the claims you made are, I would say, pretty amazing. So I would, expect physicists to immediately investigate them. If they're right, do academic physicists all over the world explore these possibilities that you've opened up?
Most people, most of the time, have some shtick about what they're doing, and unless, kicked very hard, they will not deviate from that shtick. So if you're I mean, realistically. So, like I was just this last weekend, I was on a long walk with a good friend of mine who's a top sort of physicist. And, he's interested in what I'm doing, but he's doing what he's doing. And it's kind of like I would say that there are particular subfields of theoretical physics where a bunch of people have worked on our stuff, and it's gone pretty well. It's a field where there's certain kinds of discoveries where okay, the conceptual framework is complicated enough that it takes some investment to actually get into what we're doing. And it isn't one of these things where there's kind of to mix analogies, it's sort of low-hanging fruit and the vultures start circling, so to speak. I mean, it's it's more of a, you really have to invest in the thing. I would say that if you ask the typical physicist today, are they looking for the fundamental theory of physics? Most of them will say no. That is a minority activity. It's mostly, we're working on this particular corner of this particular thing, of this particular detail, and so on. So it's not really, now, I would say that probably, I don't know, today maybe a couple of hundred physicists who are working on things that are sort of based on our physics project. So that's still a small fraction of all physicists, but the other thing that's frustrating for me, I suppose, is that if you spend your life building tooling, you get pretty good at actually figuring stuff out with that tooling. And so you see, other people are like, well, we're doing stuff on this, and I have to kind of not say too much, because I know that if I were to actually work on the thing they're working on, I can just do it in a couple of hours. And it's, so it's a complicated thing, because I built a bunch of tooling. Other people, if they get to the point where they really understand that tooling, they should be able to do it in 2 hours as well. But otherwise, they're kind of still sort of, it's more difficult. And I don't completely know how to handle that, because it's kind of a thing where I'm not going to do it all myself. And, I have some team working with me, but we're not going to do it all. And it's like, how do you do the community development to make that work? How do you, and we have this little institute that we started a few years ago that's been working on that problem. It's going quite well, but I don't think it's by the way, in terms of bizarre phenomenon. If you run a company, you're kind of delivering products and things like that. You understand how to get the flow of that to work. Doing basic science is a bizarrely different flow, and it's a fun problem to see how to manage basic science development.
All right, I think we've talked for more than an hour. I thank you a lot for taking the time to talk with us.
All right, everyone's free to get lunch, and then we'll start. Peter Walker from Carta, his talk is going to be at about 12:30-ish. Yeah.
No, just slides. Try to make it easy for you.